Good morning, Professor.
Good morning.
Good morning, sir. How are you?
Fine, you. How is going the conference?
Okay. Today we had three, yeah, two speakers. They have completed their keynote speech. Good morning, Professor.
Yes, I'm following. Yes.
So there were two keynote speeches in the morning and in the afternoon. Good morning, sir. How are you?
Fine, you. How is going the conference?
Okay. Today we had three, yeah, two speakers. They have completed their keynote speech. Good morning, Professor.
What's happening? Yes, I'm following.
Hello, Professor. Can you hear me?
Yes, clear.
Okay, now it's fine.
Yeah.
Sir, we will wait for a couple of minutes
Education
till we
is
will
the
start.
most powerful weapon which you can use to change the world. Believing in this principle, welcome to Murray Lakshman Reddy Group of Institutions,
Sir, we will wait
providing
for a couple of
world-class
minutes
education
till we will
and
start.
research facilities. Most powerful weapon which you can use to help
change the
transform.
world.
Believing in this principle, welcome to Murray Lakshman Reddy Group of Institutions,
Sir, we will wait
providing
for a couple of
world-class
minutes
education
till we will
and
start.
research
People's
lives for the better. Most powerful weapon which you can
It is the
use to help
brainchild
transform
of
a visionary
believing
who
in this
conceived
principle.
and promoted it in 2005. Meet the man, Sri Murray Lakshman Reddy, who ushered in the silent mission to Murray Lakshman Reddy Group of Institutions, a mission to
We will
provide
wait for a couple of
world-class
minutes
advancement
till we
from
start.
time to lives for the better. With the aim of imparting education with global standards, which
to
you can
enrich
use
the
to
values
help
and
transform
knowledge
a
of
visionary
students
who conceived and promoted it in 2005. The paths of Sri Murri Lakshman Reddy, making education a positive experience. Sri Murri Lakshman Reddy, Sri Murri Rajashekhara Reddy, founder secretary, nurtures MLR mission to provide to win the prize of being recognized as one among top engineering colleges in Telangana for the past consecutive academic years. To embrace the values of a visionary in vast and peaceful area of simplified paths. Sri Murri Lakshman Reddy tend to learn education about their life project. Sri Murri Centers of Sri Murri Rajashekhara Reddy founder secretary nurtures MLR mission to win the prize for being recognized as one among top engineering colleges in Telangana for the past consecutive academic years. To embrace the values of 1,000 plus motivated in vast and separate area of oil and gas. Sri Murri Lakshman Reddy tend to learn education care to life project. Sri Murri Centers of Sri Murri Rajashekhara Reddy spacious and eco-friendly canteen MLR mission to win the prize for being recognized as one among top engineering colleges. AICTE recognized MLR group of institutions accredited by NAC with A grade and has NBA accreditation for all programs. MLR Sports Complex and inaugurated by MLR Group of Institutions with most advanced multi-sports facilities like cricket stadium, badminton court, table tennis, billiards and basketball, etc. MLR Sports Complex organizes many national and international university-level sports fest by grooming every aspirant in competing national and international sports forums. Successfully achieved 50 gold medals, 13 silver medals and 16 bronze medals at various national and international sports events. MLR Group providing free admissions every year by supporting aspirant under sports quota with scholarships for the meritorious sportspersons to pursue their career in sports and opportunities in government sectors. To sharpen and extricate students' creativity and entrepreneurial skills, MLR Group has established Center for Innovation and Entrepreneurship with facilities like Social Square, Innovation Hub and Makerspace. The Makerspace is a technical prototyping platform for students' innovation and invention, which is loaded with ultra-modern equipments such as multimedia workstations, 3D printers, CNC machines, laser cutters, and thus provides stimulus for student entrepreneurs. The center has collaboration with various government and non-government ministries for raising seed fund to incubate student projects and startups. This center has developed 8 plus market-ready products and supported 11 plus student startups. MLR Group has set up livelihood business incubation in association with Ministry of Micro, Small and Medium Enterprise (MSME) to promote new technology or livelihood-based enterprises. Research and Development Cell has 12 centers of excellence in association with various industries and supports faculty and student research. It also has a track record of 25 plus funded projects, 700 plus SCI or Scopus Journal articles and 35 plus intellectual property rights, and the progress continues. In preparing the aspirants to the real-world competitiveness, MLR Group of Institutions has introduced Indo-Universe Collaboration for Engineering Education IUCEE to introduce outcome-based student-centric education and Bloom's taxonomy-based teaching, learning and evaluation process, engineering projects in community services (EPICS) in association with Purdue University, USA. Scope: School of Programming Practices to hone the coding and programming skills. Students' Platform for Engineering Education Development. Speed empowers the
Very good morning to Lorenzo Pavesi, Professor Lorenzo Pavesi, and good evening to all the participants, and welcome to the International Conference on Advanced Materials for Innovation and Sustainability, organized by the Department of Science and Humanities, MLR Institute of Technology. Today, in this session, we have a Professor Lorenzo Pavesi. He is a professor of experimental physics. He is a professor of experimental physics at the Department of Physics of University of Trento, Italy. He born on 21st of November 1961. He received his PhD in physics in 1990 at the École Polytechnique Fédérale of Lausanne. In 1990, he became an assistant professor and associate professor in 1999 and full professor in 2002 at the University of Trento. He leads the nanoscience laboratory with 25 people, teaches several classes at the Department of Physics of the University of Trento. He founded the research activity in semiconductor optoelectronics at the University of Trento and started several laboratories of photonics, growth, and advanced treatment of materials. He was the first president and founder of the IEEE Italian chapter on nanotechnology. He has directed 37 PhD students and more than 30 master students. His research activity concerned the optical properties of semiconductors. During the last years, he concentrated on silicon-based photonics, where he looks for the convergence between photonics and electronics. He is interested in active photonic devices which can be integrated in silicon by using optical nonlinearities and modified material properties. His interest encompasses also optical sensors or biosensors and solar cells. Recent development is towards integrated quantum photonics and neuromorphic photonics. In silicon photonics, he is one of the worldwide recognized experts. He organized several international conferences, workshops, and schools and is a frequently invited speaker. He manages several research projects, both national and international. He is the ERC grantee. He is a frequently invited reviewer, monitor, or referee for photonic projects, several grant agencies. He is an author or co-author of more than 500 papers, authors of several reviews, editors of more than 15 books, authors of 2 books, and holds 9 patents. He is a chief specialty editor of the section Optics and Photonics of Frontiers in Physics and founding editor of the series Photonics Materials and Applications, a joint initiative of SPI and Elsevier. Moreover, he sits in the editorial board of the ETRI Journal and of the journal Sensors and Applied Sciences. Optics and Lasers. He is in the advisory board of Glass to Power and of Sibilla, two Italian startups. In 2001, he was awarded the title of Cavaliere by the Italian president for scientific merit. In 2010 and 2011, he was elected Distinguished Speaker of IEEE Photonics Society. He is a fellow of the IEEE of SPI, AAIA, and of the SIF. He holds an H number of 60 according to the Scopus. Now, this is all about the Professor Lorenzo Pavesi. Now, I request him to take over the session. Professor Lorenzo Pavesi, thank you for joining us.
Okay, thank you very much for the introduction. And if you can leave me to share the screen. Okay, perfect. So now I can share my screen. Okay. Okay. Okay, very good. So, so thank you very much for the introduction, Professor Kumar, and thank to the MLR Institute of Technology for giving me the opportunity to come here and give you my talk on the recent activity. Before entering into the scientific details, what I would like to do is that to briefly locate where I'm coming from. So I'm coming from Trento, University of Trento in Italy. So this is Europe, and Trento is in the very north of Italy, is a town among different mountains. and therefore, so we do enjoy a lot the mountains. So this is me this weekend. But in Trento, I'm leading the nanoscience laboratory, which is a lab in the physics department. Here you see the people in the lab during our last lab meeting. And in the lab, I particularly follow three different research lines. So one is on quantum photonics, the second one is on non-Hermitian photonics, and the last one is on neuromorphic photonics. So during this talk, I will briefly introduce you those three topics. If you are interested to get more knowledge about what I did in the past, so I recently published a review on my activity in these last 30 years in silicon photonics. In addition to lead the nanoscience laboratory, I am also the director of the Quantum Science and Technology in Trento Joint Lab. So this is a lab that aims to promote research, education, and innovation in quantum technologies. And it is a joint lab between the University of Trento, the Bruno Kessler Foundation, the INFN, and the National Research Council. If you are interested to know more about this lab, so this is the website where you can have information about. So the title of today's talks is Physics and Applications Enabled by Integrated Silicon Photonic Circuits. And before entering into the details, I would like to introduce you what I mean by integrated photonic circuit. So here, the idea is to move all the different optical components that typically are observed on an optical table into a very tiny integrated circuit. And the reason why we want to do that is because by doing this, so on one side, we do get more efficient devices because we do no longer need to have a careful or a tiny alignment between the different optical components, since they are already aligned in the integrated circuit. But at the same time, so we achieve a lower noise because we get more isolation with respect to the environment, and therefore we do get significantly less losses. This will allow us to promote the mass manufacturing and widespread diffusion of the photonic circuits that we are going to realize. And this widespread diffusion is motivated by the fact that the circuit will have a much tighter, smaller dimension. They will be cheaper, and especially they will allow to merge electronic and photonics. What do we do typically in order to promote and fabricate this circuit? So the first stage is to do the design. So what we do, like an electronic circuit designer, so we do design the photonic circuits. Here you see an example of one of these photonic circuit design. And then we pass the design to a manufacturer, which produce a wafer full of these photonic circuits. Here you see an 8-inch silicon wafer full of small dies, and each one of these dies is one of the photonic circuit that we have fabricated. And then, in case we are interested to get on the same device both electronics as well as photonics, what we do is that we bond the photonic circuit with the electronic circuit. So in this way, we have a sandwich where we can manage photons as well as electrical current. Once we have the chip, then we wire the chip, meaning that we make the electrical contact as well as the optical contact. For the electrical contact, we bond metallic wire, while for the optical contact, we bond optical fiber. Once the chip is fabricated, we put the chip inside on top of a board, and in this board, we provide the electrical power, as well as we have some intelligence to manage the photonic circuit. Here you see, for example, a case that is used in order to stabilize the temperature of the chip, as well as you see the optical fibers, a microprocessor that is used to handle the different signal on the chip. So let me go back to my title. I was saying that I am interested in integrated photonic circuit, but specifically I'm interested in integrated silicon photonic circuit. So what I'm doing in my activity is to try to develop silicon photonics. And the reason is very simple. If we do use the same material as is used in electronics, so we can manufacture the photonics devices by using the standard silicon processing. And so we do not need to deploy a new fabrication industry, because this fabrication industry is already there. Therefore, we can leverage on the already deployed infrastructure in order to produce devices in large number, low cost, high volume, and with state-of-the-art performance. And finally, since both electronic circuitry as well as the photonic circuitry are made by the same material, so we can achieve a natural convergence between photonics and electronics on the very same chip. These are the motivation. So what we did in silicon photonics was to follow the same paradigm as microelectronics to success. As you know, microelectronics started just after the Second World War, and with the invention of the first transistor. And then at the end of the 50s, the first integrated circuit was demonstrated. And today, so we have electronic circuits with billions and billions of transistors integrating in the very same chip. Following this path, also the cost to produce a single transistor has dramatically decreased, and now we can afford billions of transistors in a single microelectronic chip. The same path has been followed by silicon photonics. So during the last 10 years of the last centuries, all the different components have been demonstrated. So waveguides, gratings, microresonators, splitters, and so on and so forth. Then in the first 10 years of this century, the integration has been developed. So, and now we are able to integrate in a very same photonic integrated circuit. We are able to integrate more than 1,000 of different photonic components. And today, so we are on the merge of the electronic and photonic in a very tight and single device. So silicon photonics nowadays is a platform, a significant platform. There are a huge variety of different applications of silicon photonic circuitry, for example, in optical communication, in healthcare, in consumer electronics, in data centers. And a couple of emerging technologies are in photonic computing, what I'm calling neuromorphic computing, as well as in the quantum computing. And I will show a few examples of those. But let me give you a single example of a commercial success of silicon photonics. This one is the photonic transceiver, so a device that is able to transmit and receive optical data. And here is an example of the achievement by Intel in silicon photonics. So they were able to launch on the market the first silicon photonic integrated transceiver in 2016 with a very high performance of being able to send data at 100 gigabit per second with a modulation format of PSM4. And since then, so more than 5 million of transceivers were shipped with 2 million annual transceiver sold per year. And nowadays, so the improvement, so the increase in the performance of the transistor is at such level that nowadays, so they are able to sell transceiver with a data rate up to 400 gigabit per second. So these are extremely relevant results, and the application they are targeting is data centers. So here just an example, so where the technology here is. But let me go back to what in a single lab in a physics department of a university it is possible to do. And so what I want to show you now is a few examples of new physics and potential application that are permitted by integrated silicon photonics. So here is more or less the outline of my talk. So I will start by introducing 3 simple basic building blocks, which we are using to enable the different application. Then I will show you the use of an integrated circuit for mid-infrared Gauss spectroscopy. I will introduce this concept and I will show you some data. Then I will introduce the concept of non-Hermitian photonics, and I will show you the potential of these photonics. And finally, I will introduce you a simple device that implements a neural network which can have a high impact on optical communication. So let me start. Okay, so the first simple building block that we are using is a thermal phase shifter. So this is nothing else than a waveguide where the light is channeled through, and on top of, so this is the cross section of the waveguide, and on top of this waveguide, so we deposit a metal wire. We let the current flow through the metal wire, and by the Joule effect, the metal wire heat up, which means that it also the underlying silicon waveguide. And so in this way, we change the temperature of the waveguide. And if we change the temperature of the waveguide, also the refractive index of the material in the waveguide is increased. And now, when we look at the light that is flowing through this region that we are hitting, it feels a different refractive index. Therefore, it changes also the propagation constant. Therefore, so we can introduce a phase shift in the light beam. And in this way, we can control, by controlling the current, the amount of phase shift that we are inducing. And so this is the first ingredient. The second ingredient is a waveguide, and specifically a multimode waveguide. So as you know, depending on the cross-section of a silicon waveguide, you may propagate a single mode, so the fundamental one, or if the waveguide is larger, you can also propagate the second order mode or the third order mode. And each one of these modes are characterized by a different effective refractive index. And so by controlling the width of the waveguide, we can control the number of modes that are propagating in the waveguide, which means the refractive index of these specific modes. This is the second ingredient that we need for our devices. The third one is a micro-ring resonator. So this is a very basic building block and is largely used to enable many different applications. And it's a very simple device. It's a resonator, meaning that we have a waveguide that is bent on itself. In this way, it happens that if the number of wavelengths inside the microresonator satisfy a constructive interference condition, meaning that the number of wavelengths is equal to the optical path, 2 pi times r, meaning the circumference of the microring, multiplied by the effective index of the propagating mode. If this condition is satisfied, we have a resonance for the microring. What is nice is the fact that now we can probe, we can couple light from a side waveguide to the microring resonator. And if the light is has the proper wavelength, so the light is coupled to the microring resonator, and so is propagating inside the resonator. And if you look carefully here to this relationship that fixes the resonance condition, you see that the resonance condition, once you have fabricated your waveguide, your microring resonator is determined by the effective index. Now we shine infrared light, meaning light that is not absorbed inside the silicon, but if the power of the light is large enough, so we can get 2 photon absorption in silicon. So 2 photons are absorbed at the same time. And this promotes free carriers from the valence band to the conduction band. And so we have now free carriers in the conduction band as well as free carrier in the valence band. Those free carriers thermalize, relax down in energy inside the conduction and the valence band, meaning that they are eating up the silicon, or even they can also thermalize by interband recombination, so moving from one band to the other. And also in this case, if you have interband defects, so you have that a thermalization occurs through multiphonon emission, meaning that the local temperature is increasing. And so now we have 2 effects, very interesting, nonlinear effects, that we can use to control the effective index of the silicon, meaning the resonance of the microring resonator here. One is the effect of the free carriers. So those free carriers can absorb photons, meaning that they can affect the refractive index by what is called the free carrier dispersion. And quite interestingly, the free carrier dispersion decrease. So the effect of the free carrier, it goes to a decrease in the effective index, meaning a blue shift of the resonance. On the other side, you are increasing the temperature. And the increase of the temperature increase the effective index, meaning that the resonance is redshift. And so what you have is that the nonlinear dependence, so the dependence on the power, input optical power of the refractive index, that is dictated by the rate of increase of the temperature inside your microring resonator, as well as by the rate of increase of the free carrier density. And what is nice here is the fact that those rates are significantly different. So the typical free carrier recombination lifetime is 4 nanoseconds, and the typical thermo-optical lifetime is of the order of 100 nanoseconds. And so here we have 2 knobs that we can use in order to control the position of the microring resonance. So first example of physics that is enabled by these 3 building blocks. This example is related. A prerequisite in order to move to the Gauss spectroscopy example is to generate entangled photons. And so to generate entangled photons, what we do is that we use a 4-wave mixing. So this is a spontaneous process which occurs in a Chi3 material, by which you have the 2 pumped photons spontaneously generated 2 other photons. So you have the annihilation of these 2 pumped photons and the generation of those 2 new photons. One is called the signal photon, the other is called the idler photon. And in this process, you need to conserve the energy, meaning that the sum of the energy of the signal and the idler photon should be equal to the sum of the energy of the pump of the 2 pumped photons. So in this way, the experiment that you typically do is that you pump your waveguide with a pump laser, and then you measure as the output of your waveguide 2 new peaks, which correspond to the frequency of the signal and of the idler. Here you have an example. So here is the optical power measure at the output of your waveguide in dBm as a function of the wavelength of the photons. And you get a strong pump beam because the pump is intense. And then you see here a peak that is due to the signal and a peak that is due to the idler. The sum of the 2 is equal to 2 times the pump photons. In order to get the maximum efficiency, what you have is that in addition to conserve the energy, you have also to conserve the momentum, meaning that the momentum, so the propagation constant of the two pump photons, should be equal to the sum of the propagation constant of the signal and the idler photon. And what is here important is the fact that the propagation constant, so the wave vector, depends on the effective index of the mode. And therefore, due to the wavelength dependence of, so the dispersion of the refractive index, meaning the wavelength dispersion, the wavelength dependence of the refractive index. So typically what you have is that you are getting the signal and idler photon that are generated very near to the pump photon in order to conserve the momentum. And so here is the generation efficiency, is a calculation of the generation efficiency as a function of the wavelength for the idler photon. And what you see here is the fact that if the pump is at the typical wavelength of 1550 nanometer, you see that the generation efficiency of the idler photon is very high, very near to the pump. And this you need in order to conserve the momentum. However, now, if we use not the very same waveguide modes for all the four photons, but we decide to use two different modes for the pump and two different modes for the generated new frequency, what happens is a fact that is very interesting. So what you see here is that now you get a very strong peak of generation. So you get the generation of your idler photons at a wavelength that is very different from the one of the pump. And so in this way, you can get a very large detuning between the wavelength of the pump photon and the wavelength of the generated idler photon. And therefore, by controlling the modal dispersion inside your multimodal waveguide, you can now scan a quite large spectrum of wavelength where you get the generation of these new photons. Quite importantly, the two photons are entangled photons, meaning that you get a quantum correlation between the idler and the signal photons, which are generated by this four-wave mixing process. So they are entangled in time and in energy. In time means that they are generated at the very same time. In energy means that the sum of the two energies of the signal and idler photon should be equal to the 2 times the energy of the pump photon. And now we have a tool in order to get a single photon inside our circuit. And the tool is by heralding mechanism. So the idea here is very simple. So you have two detectors. You have the two photons that are correlated in time. You measure one of the two photons, and the measurements of this photon herald the presence of the second photon inside your quantum circuit. And so in this way, you have a source of a single photon, and you are sure that you have one and only one photon in your circuit because you have detected the other photon in the pair. And so in this way, you can fabricate an heralded single photon source. And how can we prove that we have actually a single photon? So we do a very simple experiment, which is shown here in this scheme here. So what you do is that you take two detectors, single photon detector, and then you measure the coincidence between the counts of those two photon detectors, meaning you look when the two detectors click at the same time. And if you have more photons, it may happen that the two detectors click at the same time, because it may happen that one photon is going straight and the other photons is reflected. And so the two detectors can click at the same time. However, if you have only one single photon, you can never get that the two photons click at the same time, because these photons should go either straight or be reflected by the beam splitter. And so what you do is that you measure the second order correlation, so the coincidence between the two detectors as a function of the time delay between the click of the first detector and the click of the second detector. And what you should measure is a 0 click when the time delay is equal to 0. And so this means that the statistic of your photon count show empty bunch. So we fabricated the circuit. So here is the circuit that we are using in order to generate these entangled photon pairs. So here you have a waveguide. So you enter with your pump beam in this waveguide. Then you use a coupler. So you split the beam in two sides. So one side is 1/2 of the pump is going up, 1/2 of the pump is going down. And then the part that is going down is directly entering the multimodal waveguide. And on the other side, the other half that is going up is coupled through in a asymmetric directional coupler to the multimodal waveguide in such a way to excite the first order mode of the multimodal waveguide. And so in this way, you have the two pump photons, one in the first, in the fundamental, and the other in the first mode. And so those two can, through four-wave mixing, generate the idler and the signal photons. And then since the signal photons is generated in the first order mode, so you extracted the signal photon by using a directional asymmetric directional coupler, and therefore at the end of your integrated photonic circuit, so you get the idler photon here and the signal photon there. And then you measure the spectrum. And since the waveguide is large enough, so you can move the difference in the energy between the two in such a way that the signal photon is in the mid-infrared, while the idler photon is in the near-infrared. So you have separated the two very far apart. And this is actually what we have measured. So here is the signal photon, here is the idler photon, 1.3 micron, and here is the signal photon, 2 micron. And so now you have a source of mid-infrared photons that you can use. And this mid-infrared photon is entangled with the near-infrared photon. And so we did the experiment and we used this source in order to perform sensing by using the ghost spectroscopy method. So here in this methodology is a methodology by which you measure one photon, and the measurement of this photon reflects the properties of the other photon. So briefly, the technique is the following one. So here you have energy and time correlated photons, our entangled photon pairs, and then you let the mid-infrared photon to interact with the gas, and then by using a bucket detector, you simply measure the transmission of these photons through the gas. You don't do any spectroscopy measurements on that. On the other side, you measure at the same time also the near-infrared photon. And here you do the spectroscopy on the near-infrared photon. And then you measure the counts on the single photon detector caused by the near-infrared photon only when in coincidence with the mid-infrared photon that is measured by this bucket detector. And so in this way, you get several advantages. So the first one is that you get what is called the time filtering of the noise. So since you are doing a coincident detection, so you are measuring your near-infrared photon only when the mid-infrared photon has interacted with the gas chamber. And so you reduce significantly the noise because all the other photons you are not looking at. Only those photons that are time correlated you measure. The second big advantages, and this is also motivate the name ghost spectroscopy, is the fact that now you are transferring the spectral information from the near-infrared spectral range to the mid-infrared spectral range. So you see that the spectral analysis here is performed in the near-infrared, while the information that we are looking at is the absorption by the gas in the mid-infrared. And the big advantage is the fact that the near-infrared spectral analyzer are much less expensive than mid-infrared spectral analyzer. And so you can use low-cost devices to to perform measurements that otherwise will cost you a lot. And finally, since we have a very large spectral shift between the correlated photons, so we can measure in the mid-infrared by using the technology that we have already developed for near-infrared, meaning telecom spectral range. So to do the spectroscopy, what we are doing, instead of scanning a spectrometer, what we do is that we scan the pump wavelength. And by scanning the pump wavelength, so we get also a tuning of the signal wavelength, so we can scan in the mid-infrared, and we look at the idler wavelength in order to recover the ghost information. So this is the principle. Here is the methodology that we use to prove the advantages of the two of the ghost spectroscopy. So we are comparing now a standard absorption spectroscopy where we measure the transmission of the signal photons through a chamber filled by a gas, and we do that in a high environmental noisy ambient, meaning that we are shining on the detector a beam of white light, and so we are saturating the detector. So we are doing the measurement with a signal to noise ratio extremely low, 0.2. On the other side, we do the same measurements in the same high environmental noisy ambient, but now by using the ghost technique, meaning that we measure at the same time the signal and the idler. And I show you the advantages of doing the ghost spectroscopy with respect to the standard absorption spectroscopy. So here what we are doing is that we are measuring the absorption spectrum of carbon dioxide. You know that carbon dioxide has a strong vibrational mode at 2 micron. And here is the outcome of the measurements. And so we scan the pump, meaning that we are scanning the wavelength of the signal and the wavelength of the light of the idler. And then we measure the intensity of the signal light. So in the presence of a very strong noise, so the signal to noise ratio is 0.04. And so the red line here shows the results by using standard transmission measurements, while the blue line shows the results when you do the ghost measurements. You see the improvement in terms of visibility of the absorption peak caused by the CO2 is extremely elevated. When you use ghost spectroscopy, you see the detail of the spectrum, while when you use the standard spectroscopy, you barely see the absorption of CO2. In a more quantitative way, you can also measure the dependence of the transmission as a function of the pressure of CO2 in the gas chamber. So the larger is the pressure, the more CO2 you have, the larger the absorption, the lower the transmission should be. And you see that when you do the classical absorption measurements in presence of the noise, you barely see any influence in the transmission. So the transmission is only decreasing a few per mil. While if you do the ghost spectroscopy measurements, what you do see is that you see a significant dependence of the transmitted intensity on the pressure. So the information that you are able to recover is significantly larger than in the case of the ghost, in the case of the classical transmission measurements. In addition, now, if we do perform a spectral analysis on the idler photons, I remember the signal photon is the one that is transmitted through the gas chamber. So it's the one that probes the absorption of the CO2. But what we are doing now is that we are filtering, and so we are spectrally analyzing the idler photon. So the other photon, the one that has not interacted with the gas. And what we see is that the resolution of our measurements in absence of the filters is poor, while the resolution of the measurements in presence of the filter Remember, I'm filtering, I'm dispersing the hydrogen photons, is extremely increased. And what you see here is that by using the standard Gauss spectroscopy measurements without the filter, I'm not able to resolve the tiny vibrational lines of CO2. While here, by using a filter of 0.2 nanometer bandpass, I'm able to resolve the tiny vibrational mode of the CO2. This shows you the advantages of the Gauss spectroscopy method by using this source of entangled photons. So let me go to another topic, another physical concept that is enabled by using integrated silicon photonic circuit. So here the concept is about non-Hermitian photonics. And what I would like to show you is the fact that by using this concept, it is possible to produce a high sensitivity sensor. And the kind of sensor that we are using are called exceptional point sensor. So let me briefly introduce you the physics. So here the physics is the physics of an Hermitian system compared to the physics of a non-Hermitian system. So a system is called Hermitian if it shows a time reversal symmetry, or more simply speaking, if the energy of the system is conserved, meaning that the system is isolated from the environment. So in this case, you can describe, for example, a two-level system by using an Hamiltonian that is characterized by an Hermitian matrices. Meaning that if you write down the Hamiltonian, you have that the two off-diagonal terms in the Hamiltonian are equal. On the other side, you have that the non-Hermitian system is characterized by the fact that you have some dissipation within the system, meaning that the system is interacting with the environment. The energy is exchanged between our system and the environment. And this is the typical situation of a photonic system, because while the light is propagating inside a waveguide, you have that photons are lost in the path, meaning that you have a losses, optical losses in the path, and which show you that energy, photons, is exchanged with the ambient. So intrinsically, a photon, that a light signal that is propagating inside a waveguide is characterized by a non-Hermitian physics. So let's go back to our two-level system. In this case, if we are in the non-Hermitian framework, now the Hamiltonian is characterized by non-Hermitian matrices, meaning that now the off-diagonal terms in the matrix are not equal. And so this makes a strong difference between the solution of these two Hamiltonian. And actually, if we do solve the Hamiltonian for an Hermitian matrix, we see that the eigenvalues of the Hamiltonians are real values. And more interestingly, the eigenvectors are orthogonal. And so in this case, it's quite easy to show that the eigenvalues are depending linearly on the off-diagonal terms, meaning that if now I let the off-diagonal terms to go zero, so to this beta coefficient goes zero, I get that lambda 1 is equal to lambda 2. But at the same time, I get also that the eigenvectors are orthogonal. And so this condition is called in Hermitian physics, is called a diabolic point. For a non-Hermitian system, it happens that the eigenvalues are not real values, but they are complex values. And this means that now, on one side, the two eigenvalues depend through a square root dependence on the beta terms. And at the same time, we have that the eigenvectors are no longer orthogonal, but they have a projection one on the other. So this means that now in the degeneracy case, so when lambda 1 is equal to lambda 2, I have that the square root, in the case of the non-Hermitian physics, I have that this degeneracy is achieved by a square root dependence on the beta coefficient. And at the same time, in this point, I have that the two eigenvectors are equal. And this condition is called an exceptional point. And what we are doing now is that we use this condition, this exceptional point, to make a sensor. And the reason is very simple. The reason is because the energy difference between the eigenvalues as the beta coefficient is going to 0, in one case increase linearly for the diabolic point for the Hermitian system, but on the other side, it increases as a square root dependence for the non-Hermitian system, meaning for the exceptional point. And so in this case, for small values of betas, I see that I have a larger sensitivity if I'm using exceptional point than if I'm using the standard condition. And so here the idea is to try to demonstrate that actually it is possible to generate this exceptional point in a photonic circuit. And to do that, what we are using now are the ring resonators. So we have a ring resonator coupled to a waveguide. And so the typical description with the temporal modal theory is shown here. So I'm going quite fast on these technical details. So you can have all the information about that on this reference here. But what is important is that in usual actual fabricated ring resonator, you have that the surface wall are not sharp. So you have roughness on the surface wall. And this means that you have scattering of light from this surface wall. And so it happens that now you are exciting, even though you are entering only on one side, because of this backscattering caused by the surface wall roughness, what you are exciting at the same time the counter-propagating mode as well as the clockwise or the propagating mode. And so this backscattering causes a coupling, an energy exchange between the clockwise and the counterclockwise modes. And is this this counter-propagating and excitation that provide you the non-Hermitian system. However, in this case, if I only use the surface roughness, what happens is that I cannot control the strength of the coupling. And therefore, we have fabricated a structure that we call a Tahiji microresonator, by which we are able to control the coupling between the mode that propagates in one direction and the mode that propagates in the other direction. And so the idea was to introduce within the microring an S-shaped waveguide. And so in this way, so if the light is moving in this side, so you do not couple with the S-shaped waveguide, and so you do not excite the other mode. While now, if the light is propagating on this side here and can couple with the S-shaped waveguide, so we get that also the counter-propagating mode is excited. And this is a very strong consequence. So here is an example of one of our devices that have been fabricated. And the reason why we call it a Tahiji microresonator is because it resembles the Tahiji symbol. And so here you see that if we do enter from the left, in this situation, we are not able to couple to the S-shaped waveguide. And so what happens is the fact that if we enter from the left, we have a spectrum in transmission, as well as we do not have any reflection. Meaning that if we look at the light that is reflected here, if we look at the light that is reflected from here, we see that this light reflected is equal to 0. On the other side, if we enter from the right, what happens is that the light is going in, can be coupled to the S-shaped waveguide. And so we get that the light now is reflected back. And so what you see here is the fact that now, by using this Tahiji microresonator, meaning this strongly non Hermitian system. So we are able to have a device that has a strong unidirectional reflection. So if we are entering here, no light is reflected, while if you are entering in this side, a strong peak is observed in the reflection. And now we can use this non-Hermitian system, TAIJI microresonator, to make an exceptional point sensor. And here is the result. So we place a scatter, a particle on the TAIJI microresonator. And then we measure the difference between the wavelength of one and the second on the propagating and counter-propagating modes. And we see a square root dependence. If we do the same with a standard microring resonator, what happens is that now we see a linear dependence. And so here you have a system that is strongly sensitive to small nanoparticles because of the fact it is working on exceptional point. And this is the exceptional point sensor based on the non-Hermitian system that we are working on. So finally, the last chapter in these last 5 minutes is to use a photonic neural network in order to make a complex perceptron. So let me briefly introduce the reason and what is a neural network. So the idea here is to try to get inspiration on how our brain is working. So we know that our brain is extremely an extremely good device because in a very small form factor is able to make a huge quantity of computation, as well as it is a very efficient device because it's doing all this computation with a very low power consumption. This is the reason why you never lose weight only by thinking. So you have to make some sport, otherwise you do not lose your weight. And so the basic unit in our brain is the neurons. And the neurons is a threshold device, and it works in a very characteristic manner. So we have a series of dendrites that are collecting the signal from nearby neurons. All these signals are sent to the core or to the body of the neurons, where the signals are processed. If the overlap of all the signal is above a certain threshold, so then you have that the neuron is sending a signal through the axon. And this is called the neuron is firing. And so what happens in the body of the neurons is the summation of all the inputs that are coming from the other nearby neurons. And depending on the result of this summation, you have a nonlinear activation function that sends a signal to the axon. Then this signal is processed by the other neurons that are performing exactly the same function. So collecting signal from other neurons. If the overall sum is larger than a threshold, the neuron fires and the signal is sent to the other neurons, and so on and so forth. And this is the way we are thinking. And so what we did was to develop an optical neuron. So a device that is able to receive signals from the input, so multiple input. Then we have a body where we do a weighted sum, and then we have an activation function that is producing an output. Now, in a neural network, what we are doing is that we are changing the weight in the sum in such a way that the output is what we are desiring. For example, we want to have a neural network that is able to distinguish a dog or from a cat. And so what we are doing, we are teaching the neural network to distinguish the dog. And the way we teach the neural network is to change the weight so that the output is high only when the input corresponds to a dog. And so what we did was to use exactly the same principle of the neural network integrated in photonics in order to perform some functions that are useful for optical communication. And so the kind of device that we are using are very simple: optical coupler, so two waveguide merge, and this gives us the possibility to the sum. We use the phase shifter in order to change the phase of the light, And this provides us the possibility to teach to the neural network to perform given function. And then finally, the simple operation of detection, where we have that the detector is answering, is sensitive to the intensity of the field, meaning the square root of the electrical field, give us the nonlinear function for activating the threshold. So this is the principle. Here is the very simple device that we have developed. So we have an input, a bit stream that is coming and is input into the device. And then we have 4 different waveguides. And along each one of these waveguide, we insert a delay line in such a way that now we have 4 versions of the input at different time. So we have the present time, the past time, the 2 past time, the 3 past time. And then what we do is that we use phase shifter that are trained by the answer. Depending on the answer, we train this phase shifter in order to change the value of the sum. Here you get an interference between all the different delay copy of the signal that is propagating within the perceptor. And so we have we can control the interference that is occurring on the output. And then the detection gives us the nonlinear function. So essentially it happens that the present state of the output depends on the present state of the input, a delayed version of the input, a delayed version of the input, and a delayed version of the input. And what we do is that we can control the relative weight of those delayed version of the input in the output, depending on the training process. And so this is the idea. Here are some results. So this is a simple device, and we have teach this simple device to learn to recognize a given pattern in a sequence of bits. And so here the idea is to detect the pattern 1, 0 in a sequence of bits that are input at 16 gigabit per second, so extremely fast bit rate. Here is the trace. Looks, this is time scale. Here is a picosecond. And so here, for example, you have the blue line is the input. So you have 1, 1. And so 1, 1 does not correspond to the pattern. And so the output should stay low. While here you have the proper sequence. So you have the sequence 1, 0, 1, 0. And now the output of the network should recognize the pattern and should rise a flag. And so the outputs should go high. And here you see that the output is going high. Here you have 1, 1, the output is 0. You have 0, 1, the output is 0. But here you have 1, 0, so the pattern that you want to recognize. And so the output now is going high. And so what happens is that our neural network is able to recognize this pattern 1, 0 at 60 gigabit per second. And each time the pattern is the one that he has to recognize, it rises a flag. And it can do that for 2-bit patterns and even for 3-bit patterns, an extremely high bit rate, 16 gigabit per second. And so this is a simple function. Here we are using the network to perform a more complicated pattern function that is very important for optical communication application. So here you have an input bit stream, the typical optical data that you send on an optical fiber that is propagating through a fiber length of 100 kilometers. And then due to the chromatic dispersion, you have that now the output from this fiber is distorted. So since you have chromatic dispersion, now it's very difficult to recognize the 1 of 0 from the 0. And so you have that your signal is degraded. And so what we are doing is that we are using our neural network in order to recover the signal so that to achieve at the end of the neural network exactly the same signal that we had at the input of the optical fiber. So in this way, what we are doing is that we are using our neural network in order to mitigate the chromatic dispersion of the optical fiber. And what we want to do that, we want to do that at a very high bit rate, for in this case is 100 gigabit per second. So this is the actual output. Here you see the blue line is the input. you see the orange line, that is the output without the neural network, and the yellow line is the output with the neural network. And what you see here is that the neural network is able to recover the input signal. And this you can quantify by computing the number of bits that are wrong with respect to the number of bits that has been transmitted. So the smaller is the bit error rate, the better is the performance of your network. From a point of view of the telecom provider, what they are doing, they are increasing the power, because by increasing the power, you increase the signal to noise ratio, meaning that you are able to recover better the results. And so this is what is observed. So the bit error rate, so the number of bits that you are computing wrongly, so you are recognizing wrongly, as a function of the power received to the sensor, you see that the number of bits that you are recognized wrongly decrease significantly as you increase the power that you receive. But increasing the power means that you need to provide more input power, meaning that the whole transmission is cost you much more. What you see here is the effect of the neural network. This very simple neural network can get a very low bit error rate at a much lower input power, meaning that is allow you to use a much smaller input power. And so here you see that you get an improvement in the performance of the optical link of several dBs. So from here to there, you have 5 dBs. So you get an improvement of 5 dBs by simply using this neural network, meaning that by using the neural network, now you are able to equalize the transmission. So I'm concluding now. So I hope to have shown you a few examples of the physics application of silicon photonic integrated circuits. I hope to have shown you that also very simple structure are able to show very interesting phenomena and powerful application. I think that there are a huge room for improvement if we now move from simple structure to a more complicated structure by, for example, forming complicated matrices of these building blocks. So I would like to thank the people in my lab that have done all this work. So if you are interested, so this is the link to the website of my lab. I should acknowledge the people that have funded these research activities, mostly European Commission. And if you are interested, here a few references of the books that I have edited in the past. Thank you very much for your attention.
Thank you, Professor. Thank you very much. It's a wonderful presentation. You have covered several topics, which includes mid-infrared sensing to ghost spectroscopy, and you also introduced the non-linear Hermitian system, non-Hermitian system for the strong unidirectional light transmission. You also discussed about the introduction of the neural network in the devices to overcome the losses of the light. Losses of the signal. So thank you very much for your presentation and for accepting my invitation.
Thank you to you. So if you want, I can send you the
Professor will take up some questions if there is any. Hello, Professor.
Yes, I'm here.
Yeah. So in S-type ring resonator, will you observe the whispering gallery modes?
Exactly. So in this kind of resonator, I do observe different kind of modes that are the one that are propagating along the input direction, and the other that is counter propagating along the input direction. Yes. But the physics is the physics of the whispering gallery modes, yes.
Okay.
Exactly.
So what is the exact problem with the surface roughness? What is the effect of the surface roughness on the whispering gallery mode?
Okay, so the effect is the following. So once you have a light beam that is propagating in a waveguide, and if the waveguide show roughness, you have that the photons that reach the surface can be scattered back.
Okay.
And so that means that if you are exciting in a micro-ring resonator or in a whispering gallery mode structure, if you are exciting a clockwise mode, due to the surface roughness, you excite also the counterclockwise mode. And so you have energy that flow from the clockwise mode to the counter clockwise mode. Yes. And this is you are trying to, you are willing to excite a single mode, but due to the scattering on the surface wall, you excite both the clockwise and the counterclockwise mode.
Okay. Okay. Thank you, Professor, for your wonderful presentation.
Welcome.